The next speaker here in the booth is Dr. Jani Kiuru, who will be telling you about how does water savings relate to process industry and what kind of effects the water savings can have, advantages, disadvantages. And Jani, floor is yours.
Thank you, Tuomas. Ladies and gentlemen, I will take a slightly more practical viewpoint to today's topic, and I will start by briefly describing the kind of the challenges and benefits what could come out when you are using water footprint, for instance, in reducing water consumption in industry. And then I will show some examples from VTT studies how these issues can be managed and what kind of consequences there might be. And in the end, I will repeat myself and tell this all over again in the summary. Minister Niinistö already covered the statistic quite nicely. As he said, the industrial usage of fresh water is slightly a bit more than 20% of the total fresh water consumption in the world. But of course, if you take or add up all the reused water as well, this share increases significantly. And the challenge here is, of course, that the water consumption is expected to increase. And where is the water then used? Helena later today will come back to this issue. I will just shortly list the main usages of water in process industry. Material is easier to transport in liquid form, and therefore water is used basically to dilute the material for transportation, for pumping. And of course, for shower waters, shower in process industry means probably a bit different thing than in households, but it's like wetting, trimming, for instance, in paper making, trimming the web, cleaning and anti-foam purposes. Then cooling water, there are cooling systems in almost every industrial process. And the other side of the story is the steam production, heating and drying. Water is used there as well. And then sealing water for pumps and of course for cleaning. Good thing in reducing water usage is that there are several advantages as well. Without these benefits, there would be no sense to do that. I have here divided these benefits into three categories. First one is economical advantages. This basically means that you are using less water. Water has some price, and therefore it's economically attractive to reduce water consumption. This is also related to the treatment of the fresh water. It costs as well. Then from the process point of view, in principle, water recycling enables more stable operating conditions. This is mainly related to temperature, which I will come back later. Then, of course, when you recycle water, you are also able to recover all the materials that has gone with the water. So therefore, from process point of view, you also can achieve lower material losses. And in some processes, drainage improvement as well, meaning productivity, which is again related to temperature mainly. And from environmental point of view, you need less natural resources, meaning water, and at the same time, you will have less effluents back to the environment. And of course, the energy savings, you don't have to heat up water and pump it so much. In other side of the story is the challenges. There are not only benefits. As I said, material tend to accumulate in the water cycles once you start closing them. And Then there are suspended solids, and there are also dissolved and colloidal substances. These affect to the productivity, and moreover they affect to the performance of different functions in the process, meaning, for instance, chemicals function differently when there are these so-called detrimental substances accumulating. And temperature increases challenge as well, since, for instance, microbiology may become an issue when the temperature settles in the convenient point for microbes to multiply. Then to the examples. I will look these examples from physical, chemical, and microbial point of view, and show that this whole area is really complex. And I will start with the physical one. So if you have water system which is not closed at all, of course your freshwater quality varies, and you will have certain problems coming from the fresh water. But if the system is not closed, the problem comes and it goes away with the water. But when you start closing it, the same problem comes over and over again. And then we are talking about certain type of oscillation. In principle, it fades away when new water comes in, and it kind of dilutes the problem. But since the system must be controlled, there are certain control loops which try to compensate this problem by chemistry, by physics, by various types of activities. These oscillations tend to increase, and this is a typical physical increasing oscillation curve shown in the figure. And at some point, the process cannot handle it anymore, and it leads to problem, in this case, into a production break. Next example is the chemistry part of the issue. This is an example from a paper making process, and there, in the beginning of this monitoring period, the system was closed, not totally, but the closure was increased, and it led to the accumulation of dissolved calcium into the process, as shown in the figure in the middle. This, of course, increased the conductivity. The salt content of the process increased, which then started to affect to the chemical balance of the system itself, which is shown in the lowest graph here. The charge started to decrease. This means that the anionic compounds and these salts started to accumulate to the process, and this is called anionic trash in the process. It then chemicals added does not work the way they were designed to. This anionic load increases the uses of chemicals, and you really have to redesign the system from the scratch, basically. This just emphasized the complexity of the issue. Then to the temperature part. This shows that, of course, usually when you take water into the system, the temperature of the water is lower compared to the temperature of the process. And when you circulate the water, the temperature keeps increasing all the time. And for some reason, it usually settles around 40 degrees of centigrade, which is more or less the perfect conditions for microorganisms to build up. And when that happens, they consume the oxygen away, and in the next slide I will show what it means in practice. Also, speed of reactions, which is called corrosion, increase. Deposit formation increases. Also, some material characteristics change, which might mean, for instance, that the stickies get loose and then they are found somewhere else in the process, causing problems. Salt solubility increases, which means conductivity increase, for instance. Also, salts are related to corrosion. And then the physical part of the problem is that the vacuum capacity decreases, affecting the suction boxes, pumping efficiency, etc. This is an example of how microorganisms build up in the process. In all the water-intensive processes, at some point you have to store the water. It might be due to that you just don't want to throw the water away, or there's some break at the production and you cannot use the water. And when it's recycled water, it does contain this organic material I already told you about, meaning dissolved colloidal material, organic compounds added to the process, or organic compounds coming from the particles that are used for product, for instance, fibers in paper making. And when that type of material is stored, the microorganism starts to build up immediately. And this example shows that just a few hours of storage, basically all the oxygen is consumed from the process. Then the redox potential starts to decrease, and these reductive reactions start to decrease the pH due to acid formation. And these acids are usually smelly compounds. There are smell in the process and also outside the process, and also the product starts to spoil, and of course all the conditions change, which means that the process cannot be driven as it's designed to. And as also shown here, this all can be fixed by using biocide, but biocide has a price. Of course, price as a money, but also price that it also affects to the process. It is usually a salt itself, and it causes another problems. Then to the summary. So most of the problems or challenges related to this closure is related to controlling the system and how the system varies. If there's a lot of variations, the process is difficult to control, because if you, for instance, do some change, it disappears into the fluctuations and you don't know what the effect is. So the key is to minimize these type of variations and optimize the process. Also related to the chemical interactions, so you have to optimize the process with the chemicals, because usually after closure you cannot use the same chemicals you used before. And also there the interactions are really complex. It's really difficult to figure out which is a cause and which is effect, which should be adjusted and which should be just monitored. But if this task is being carried out properly, there's a potential to turn these challenges into advantages. And how? Well, you must have seen this coming. Research. So process optimization is not a simple task. It's a combination of measurements and analysis. You might even have to develop those to overcome these challenges. Then probably use modeling, and of course always expertise related to that process is needed. And well, there are some technologies that would help. For instance, separation to get rid of these accumulated materials, to design new chemical system, design even new chemicals, and of course monitoring, also monitoring of the phenomena that cannot be currently monitored, or even design a new unit process to tackle some issues. And then in this last slide, I will finally mention the word water footprint. So as Elina just told you about the footprint, it's really a good tool to show the potential to decrease the water consumption or improve the quality of the effluent or anything related to water usage in the processes. So with that tool, you can show what is the potential to do that. But after that, it's really work. First, you have to find out kind of the pollution or detrimental substances that are being introduced to the process due to, for instance, recycling of the water. And that is basically simply just measuring and analyzing it. And then checking the possible treatments for each stream. So what you need to do for the recycled water in order to be able to use it. And that's slightly more complex. Probably you need to model the system and test different kind of flows and applications in the lab. And then finally specifying the necessary water quality for different uses and design what water you can use and where. And this is then probably phenomena modeling and carrying out the activities in pilot before applying it into the full scale. So reduction of water consumption is possible without affecting the product quality or process. And by properly designing these activities, there are really significant benefits, economic and environmental. Thank you for your attention.
Thank you, Jani, for the presentation. So smart water use also means how to control water-based processes in a clever way.